Everyone, and welcome to this explainer. Today, we're setting the stage for a truly cinematic journey into the intelligent, honestly almost invisible infrastructure of 5G. And look, we aren't just talking about getting faster downloads on your phone. We're looking at a complete architectural marvel. We're going to break down the highly technical blueprints, straight from the global standard makers themselves, to really understand how data moves from this massive global vision, all the way down to the absolute velocity of a single microscopic data pulse. Let's dive in. I want you to really think about this for a second. How can a single invisible network simultaneously handle the massive bandwidth of an immersive 8K virtual reality stream, the absolute zero margin for error precision of a robotic surgical scalpel, and the sheer volume of 1 million smart agricultural sensors reporting in from a massive farm? In the past, these wildly different resource demands would absolutely require completely different specialized networks. But 5G? It does it all at once over a shared physical infrastructure. Today, we're going to uncover exactly how it pulls off this incredible balancing act.
All right, Phase 1, the architects of the global vision.
Okay, so let's look at the actual standard makers who built this. It all starts with a huge global vision set by the ITU. That flows right through technical protocols, like 802.11 from the IEEE, and it utilizes these invisible spectrum lanes organized by the FCC. Together with organizations like ETSI, that's the European Telecommunication Standards Institute, and 3GPP, these global architects are basically writing the glowing digital blueprints for the entire planet. The technical specifications they write, like the TS123501 document we're analyzing today, are the master code. They ensure a 5G cell tower in Tokyo can flawlessly talk to a robotic assembly line in Berlin. But to actually make this global vision work, these architects had to fundamentally rewrite how a network operates. According to the 3GPP standards, the 5G system, or 5GS, leverages software-defined networking. Now, the absolute crucial part of this definition is the separation of the user plane from the control plane. See, in traditional telecom, the brains making the routing decisions and the brawn actually moving your data were locked together in heavy, expensive hardware. 5G completely decouples them. This is called control and user plane separation, or CUPS. By turning network functions into software, operators can scale the brains and the brawn totally independently, pushing them exactly where they're needed most. Moving right along to Phase 2, the 5G service triangle. Since the whole network is software-defined, it can basically slice itself up into these dedicated, invisible highway lanes for totally different uses. The standards define these as slice, or service types. Value 1 is eMBB, which stands for Enhanced Mobile Broadband, so that's your high-speed internet. Value 2 is uRLLC for ultra-reliable low latency. Value 3 is MIoT for massive IoT, and Value 4 is V2X, meaning vehicle-to-everything for smart cars. What's wild is that a single physical cell tower hosts all these logical slices, keeping their data completely isolated and perfectly optimized. Now, to really grasp the brilliance of 5G, you have to look at this extreme trade-off in resource allocation. Because, well, not every device needs everything. eMBB demands massive bandwidth. We're talking up to 20 gigabits per second for things like immersive 8K VR streaming. But it can tolerate a tiny bit of buffering. uRLLC, on the other hand, demands instant 1 millisecond latency. A robotic arm performing surgery definitely doesn't need 20 gigabits of data, but if that tiny data packet arrives even a millisecond late, that's a total disaster. 5G shifts its resources intelligently based on exactly what the specific device needs.
Let's zoom in on that uRLLC slice for a moment. The 3GPP defines it simply as a slice suitable for the handling of ultra-reliable low-latency communications. Sounds simple enough, right? But the engineering behind that sentence is mind-bending. To guarantee this literal life-or-death reliability, the 5G standards actually allow a device to set up 2 redundant data sessions over completely disjointed network paths. That means if you're in an autonomous vehicle and it needs to hit the brakes instantly based on a network signal, the network duplicates that signal across 2 separate paths. It ensures that even if one path has a micro hiccup, the critical braking data still gets through instantly.
Okay, Phase 3, slicing the core and the edge engine. Let's actually track a data pulse right into the heart of the network. Step 1. Your device or user equipment initiates a pulse. Step 2. It hits the radio access network. But remember, in 5G, the cell tower is disaggregated into 3 specialized parts. You've got the RU, or radio unit, at the top, the DU, or distributed unit, nearby, and the CU, or centralized unit, further back. Step 3. Once it passes the RAN, traffic is dynamically steered to the optimal user plane function.
So what exactly is this user plane function, or UPF? Well, as the definition says, it handles user data traffic and routes it through the core. And this brings us to a really massive takeaway, what we can call the core insight. Because the 5G core is service-based, it acts as a shape-shifting engine that seriously doesn't care about the hardware at all. It only cares about the specific network slice. The exact same core infrastructure can act as a massive, high-speed pipe for a smartphone streaming a movie and simultaneously act as a highly specialized, hyper-reliable link for that surgical robot. The UPF is the ultimate flexible traffic cop, making this whole thing happen.
And that brings us to the RAN insight. By combining that separation of the control and user planes with multi-access edge computing, 5G does something incredible. It moves computing power right to the edge. The distributed unit, or DU, handles time-sensitive radio scheduling right at the tower. By bringing the network's brain closer to you, the physical distance the data travels is shortened drastically, which is exactly how 5G slashes latency to almost zero.
On to Phase 4, right-sizing with NR-RedCap. So, as these standards evolve, the architects hit a massive wall when it came to cost and power, specifically when trying to connect millions of simple IoT devices. To solve this, 3GPP Release 17 introduces an incredible breakthrough. Enter NR-RedCap, which stands for Reduced Capability. This is our key standards insight. Think about it. If you're deploying, say, 50,000 smart moisture sensors across a massive corporate farm, you cannot afford to put a premium, power-hungry $1,000 smartphone modem inside every single sensor. It just doesn't work. RedCap is a subtype of 5G radio access that specifically solves this cost and power problem. It's the ultimate trade-off. It provides just enough of that 5G pulse to stay connected to the network, but bypasses all the extreme bandwidth features. This dramatically lowers the cost of the chips and enables remote smart sensors to achieve up to a 10-year battery life on a single charge, all while still riding on that exact same shared 5G infrastructure.
Which brings us to the future of velocity.
I want to leave you with this final thought today. 5G isn't just a faster pipeline. It is a radically flexible, software-defined ecosystem. As this invisible infrastructure intelligently shapeshifts in real time to power everything from immersive 8K realities to microscopic robotic precision, we really have to ask ourselves, what unimaginable new worlds will we build on top of it? The foundation is laid, the network is sliced, and the velocity is definitely here. Thank you so much for joining me on this explainer. Until next time, keep learning, keep questioning, and keep exploring the infrastructure of tomorrow.